Today we are going to discuss something that is the second part of the transient and harmonic analysis video, that is the harmonic analysis. First of all, for harmonic analysis, you have to wait so that the system can reach steady state condition. So, obviously, you have to wait for certain time, even if you do not know what is the exact time constant of the system and can calculate that time required to system to reach within a particular band. You can do what? You can wait until your curve, whatever you are getting in your oscillogram, is becoming. Suppose this is your sorry. I think I can get some help from here also. Anyway, so let me draw it without wasting much time. That it is like, if this is your oscillogram window, then before your system reaches the steady state condition, if this is your horizontal axis, your curve will be like something like, it will not become symmetrical with your axis, right? It will be like this. In this way. But if you wait certain time, then you will see that it is repeating a continuous pattern. So when you will find that your curve, the response curve has reached such a stage where it becomes almost a period, means it exhibits the nature of a periodic signal. A periodic signal cannot be asymmetric with respect to its horizontal or independent variable axis. Periodic signal variation must be symmetric with respect to its means independent variable axis. So you have to wait till that your means the variable you want to observe, that response becomes symmetric with respect to the horizontal axis. Okay, so if that is the case, then what in a single line we can write, we have to wait and start exhibiting a periodic Well, so if that is the case, then where is that? Okay. So if that is the case, then so we got some answer that how long an individual should wait so the system reach its steady state condition. So steady state is mandatory for harmonic analysis. Now what you will do for after reaching the steady state? First of all, for non-periodic waveform, sorry, not, yeah, for non-periodic waveform you cannot do harmonic analysis. That is why it is not possible for us when the curve was asymmetric with respect to our horizontal axis, we couldn't carry out the harmonic analysis. But as long as the curve approximately maintain a symmetry with respect to independent axis, we can proceed for harmonic analysis. Harmonic analysis is valid for non-sinusoidal periodic signal. Now, unlike musical instruments where you can uh, generate a particular frequency sound by your own means at your own discretion, you can generate uh, frequency, any frequency sound. Here the case is somewhat different. Here what happens, whenever in machine, electrical machine, we get harmonics, so that harmonics is due to the construction or physical constraint of the machine. Our sinusoidal supply, or even when the machine is operating with sinusoid, the voltage, some of its parameters may become non-sinusoidal. Let me give you one example. But before going to that, in machine, another interesting thing we observed regarding harmonics, one is space harmonics and another one is time harmonics. So this time harmonics is the signal that is having different frequency, and that is why the different frequency signals can complete different number of cycles within a single span of time. Within, if you consider say 10 seconds, then if one fundamental can complete one cycle, then the fifth harmonic can complete 50 cycles. It is like that. And similarly for space harmonics, giving a particular radian and angular span, say 0 to 2 pi, if your fundamental waveform can execute a single cycle, your fifth harmonic will have fifth harmonic will have 5 cycles within that same span, and seventh harmonic will have 7 cycles in that same span. So what we can understand here, but let us first start with time harmonics, because time harmonics is easy to visualize, and obviously in your other circuit theory or other classes you must have heard about time harmonics. So let us start with time harmonics. So for a non-sinusoidal periodic signal during its steady state condition, we can find out the either we can find out the space harmonics or we can find out the time harmonics. Now, while dealing with harmonics, we will find out a few things, that is the symmetry and order of the harmonics. So when we are talking about symmetry, then as we know that if a function can be written like f of x is equal to then that is a function with even symmetry, like cos theta is equal to this is a function with even symmetry. And then actually my mouse is not working, so I have to manage it with this pen tablet. Yeah. So, and what is odd symmetry? Odd symmetry is f of x is equal to like sine of minus theta is equal to minus sine theta. So I would like to show some example of that. Now here, one thing we must keep in mind that even symmetry and odd symmetry exist in periodic as well as in aperiodic function. Like if we plot our, just let me check. Yeah. If we plot our x data along our horizontal axis and y data along our vertical axis, then if we get any curve like this, say y is equal to some, where k is a proportionality constant. This is an example of even function. We can have this is also an even function, right? So how to identify even function, and also periodic even function includes like if we can have it like yeah, periodic even function includes like cos theta, this is an example of even harmonic. And also if you have so one thing we can basically we can make it very clear, even if it is periodic or aperiodic, whatever be the case, you can always find that for even function, if you plot them, obviously for aperiodic function, their curve may be out of bound, but if you plot cos x in this yx plane, what you will get? You will get for different value of, yes, you will get it like this. Now the point here is that for even function, okay, before I discuss more on even function, let me draw one example of odd function. Like instead of y is equal to x, if you y is equal to mod x, if you just make it y is equal to x, then it will become an odd function, right? So similarly, what about the periodic odd function? Sine is an example of periodic odd function. Now here, one thing we must understand that in case of our system, electrical machine, when the presence of nonlinearity can distort a sinusoidal signal in form of a non-sinusoidal signal, in that case it is very difficult to ensure that your input signal symmetry will be preserved. What I am trying to say, forget about nonlinearity. Even if you have a nonlinear element, suppose you have a circuit where you are having this, okay, don't go to the circuit because you will again get confused. Here, one thing is very clear, that if we change it, like it all the even symmetry and odd symmetry, I am not talking about order, I am talking about the waveform evenness and oddness that is defined by this formula. Here you can see that all these depend on only this part, f of x is equal to f of minus s and f of x is equal to minus of f of minus x. If all this happen, then that is even and odd. But here this even and odd for periodic waveform also depend on their phase. Like if you have something that may introduce a phase shift, like let me draw one circuit, two circuit rather. Here you have a if this is Vm sin omega t, then your waveform, the supply is having odd symmetry. Here also you are having the current, what? Odd symmetry. However, if we place it or although the voltage will remain odd symmetry, but current will start exhibiting even symmetry. So basically what I am trying to say, this odd and even symmetry of harmonics is not that important for electrical engineer, rather the odd and even order of harmonics. Obviously, this also sometimes it plays an important role while we try to figure out that whether we are having only the sine terms. Sine terms means all odd order, not order, rather all odd symmetry harmonics are present in my system, and if we consider the waveform, it is exhibiting such a case that it may contain some kind of even symmetry also, then we have to decide. But before that, we need to understand that non-linearity or non-sinusoidal, that non-linearity that can cause distortion in our sinusoidal waveform. We must have a detailed study on them. Now, what I would like to highlight here, let me first draw the diagram a bit clearly so that you can see it. This type of nonlinearity is called relay nonlinearity, right? So in relay nonlinearity, what we are getting, we are applying a sine wave, right? And that sine wave produces sine wave produces a square wave. See here the time when the sine wave started. And when the square wave started, both are means same time axis. At t is equal to 0, sine wave started. At t is equal to 0, square wave started. So if we extend it in this way, in this side also, by drawing another means half of your sine wave, then what you will get here, you will get exactly a reciprocal of this. So if it is the case, then what we can say that for this kind of nonlinearity, that is we are getting that if our input is having odd symmetry, output will also have odd symmetry. Now, let us take another example. This one is quite legible. This is known as backlash nonlinearity. Again, we are passing some sine wave, but what we are getting? We are getting another distorted non-sinusoidal waveform shown by this yt. However, one thing you must notice that here, although their starting time is not same, however, if we just draw another extension of this curve, like by doing this, then what we will see, it also become first, for some time it will become means for this period it will give 0, and then it will start reciprocating like this. So basically what I am trying to claim that, no, not, sorry, not, it is not backlash, I made a mistake here, it is dead zone. And dead zone is also common in motor. What is dead zone? That suppose you have, even in your electric bulb also you can observe dead zone. Suppose a bulb, it is rated, a tungsten bulb, filament bulb is rated for 240 volt. Now obviously you know, until unless the bulb cross its dead zone voltage, you do not get any output from the bulb, right? So that way you can visualize the concept of dead zone, that it is the minimum value of the input below which your if your input value falls below the dead zone value, here shown by this delta, your system won't produce any output. Okay, so even this is dead zone nonlinearity. If our input is having odd, output is also means preserving that odd symmetry. Now here let us show us another one. I am showing you all these pictures so that you can understand it clearly. Which one? Yes, this is for relay, already shown. Yes. This is called saturation nonlinearity. Here also you can see that even if the output is distorted, the output is prevailing the symmetry of the input waveform. Input symmetry, output symmetry, both are having odd symmetry. Now, if we just revisit them, what is common there in all this nonlinearity, in these three nonlinearity, this plane, here this plane is our, this side is for our input, and this vertical line is for output. So in input output plane, if we see all these nonlinearities, here you can see that all the nonlinearities are represented by a single line. So this type of nonlinearity, we can say that if any nonlinearity that can be represented by a single line in your input output plane, then it is a piecewise nonlinearity, and also it piecewise nonlinearity, in addition it is memoryless nonlinearity. It doesn't enclose any closed path in your input output plane, and hence it cannot alter the symmetry of the input waveform. If your input is having even symmetry, it will preserve that symmetry in your output, although output will get distorted due to the presence of this nonlinear element, but the symmetry won't be affected. Now we will move to our next type of nonlinearity, that is hysteresis. So what is hysteresis nonlinearity? Let me show you. Hysteresis can occur anywhere, not only in your transformer. A different form of hysteresis can take place. So let me show you one example of hysteresis nonlinearity. Yeah. It is a relay with hysteresis. Previously, we observed that relay, that is like having input output, and now this one is relay with hysteresis. Now, see what we can focus here, that in this relay with hysteresis, here, due to the presence of hysteresis, now whatever symmetry our input waveform is having, input is still sine wave, that is having an odd symmetry. But see, this is the starting point, t is equal to 0. Now, if you draw this line here, here, you will see it is like that. That means when your t is equal to 0 is starting, and it's so you may argue that, sir, in case of dead zone also you show us that input and output starting point doesn't match, but in that case you claimed the symmetry is means input output symmetry remains same. However, here you are claiming that input is, even if the input is having odd symmetry, output will have even plus odd symmetry. Why so? The answer is that if we go back to the dead zone page, then you will see here in dead zone it is no output is there. Therefore, the symmetry prevails. But here, if you see, you will see that here there means all the time the output waveform is there, but it is with this output, if you even draw it clearly, then also you cannot, if this dotted line indicates my t is equal to 0, then with respect to this, neither you can claim that y t, or you can write it y omega t. Y omega t is minus y minus omega t, that is true for sine wave. Neither you can write it y omega t is equal to y of minus omega t, that is true for cosine wave. Nothing you can write for this, because here the output waveform has lost its particular even or odd type symmetry. It is neither even nor odd, right? So what is the difference here? Here, if you see here in this input output plane, the nonlinearity form a closed curve. Similarly, if you consider our very own BH curve, you will see that as long as saturation is there, BH curve doesn't form a closed loop in your hysteresis plane. However, when we are considering hysteresis is present, then BH curve forms a closed loop. So that is the difference. If we have, here it is also a piecewise linear system, but if we have a piecewise nonlinearity with memory, then So from electrical engineering perspective, this even and odd symmetry doesn't play so much important role, because if your hysteresis is present, then that will alter the symmetry. So basically, if we ask ourselves that is it so important to understand, uh, sometimes the answer may be yes, sometimes the answer may be no. So we would like to form or find out another type of symmetry that at least won't get altered due to the nature of the nonlinearity present in our system. So while we search for that kind of nonlinearity, or form that kind of symmetry, we come across half-wave symmetry. What is that half-wave symmetry? Let me explain. Now, what is the essence of observing any type of symmetry? Because if we can observe, then we can discard either all sine harmonics or cosine harmonics from our representation. But even if we cannot discover any particular such even or odd symmetry, we can have half-wave symmetry present in our representation. This half-wave symmetry, first of all, what is half-wave symmetry? That is like, if you have a waveform like this, you can write half-wave symmetry is, if a system is having half-wave symmetry, or if you want me to write it in yx, so what I wrote here, I just wrote it here. So let me just explain it. See here, if you see the waveform, it is this one is 0 to t. It is taking this much time to repeat itself. Now we are having, this is our t by 2. So this doing this t minus t by 2 means what? This t minus t by 2 means you are offering a lag to your means waveform, and then what you will observe, that if you do this, you will get a half-wave symmetry like this. Now, the essence of this half-wave symmetry, what is the essence of this half-wave symmetry? That if your system is having this half-wave symmetry, we can mathematically prove that only odd order harmonics will be present. Now I do know that you people have many confusion regarding odd symmetry and odd order. Let me show you something. Okay, this will make you a bit confused. Let me just search for a easier diagram that you can understand. This is this is a very beautiful example. You can understand the difference between the harmonics, like order and the symmetry of the harmonics. Here, the waveform is having even symmetry. This solid blue line is for resultant. This green one is showing the fundamental. Then what about uh, this one? This here you can see this is executing how many number while it is completing one full wave. Here if we calculate, if we start our calculation from here to here, how much? The one, two, one, two. This is a third harmonic. I am a bit color blind, so I cannot see that this one, that exact color. And this one, how many it is executing between these? One, two, one, two, three, four, five. Okay. The small one is fifth harmonic. So you can understand here, although your system is having even symmetry, but you can have harmonics of odd order. Same is true for sine wave. Only problem is that you cannot draw any waveform without or completely means discarding the information about fundamental harmonics, and fundamental harmonics is definitely an odd harmonic, so you have to draw it. But here it is one example where we can see that even if it is a even symmetry function, but it is having all odd order harmonics, and if you want to test whether this is fulfilling the half wave symmetry, let us test it here. If this is having half wave symmetry or not, let us test it here. So this waveform, what is the half period like here to here? Let me draw it by shifting the half period, like this one should be shifted from this is pi, so this shifted this should be shifted here, so let me draw it. Okay. Then accordingly the rest of the things can be drawn. It is becoming a bit more healthy than that of word. So you can get some idea that it is preserving the half wave symmetry, and that is why only the odd order harmonics are present here, right? So this is having the half wave symmetry, and the most important feature of this half wave symmetry is that even if you consider hysteresis, here see this waveform, this everything is distorted, means it has distorted its fundamental nature of the symmetry, but this half wave symmetry cannot be distorted by any phase shift offered by your nonlinear element. Like what I am trying to say, that had we considered only a memoryless nonlinearity, like which one I just discuss it here. In case of memoryless nonlinearity, this waveform, this square wave, was having a half wave symmetry. If you want, you can just shift it and construct it, or even if you ask me, then I can also construct it for you. Like if this is our half period, then we should shift it, like this is the complete period, so this is our half period, not this one. This is our half period. So if we need to shift it, then the shifted waveform will be like this, right? It will be shown by the dotted line. Always the square wave preserves the half wave symmetry, and no need to draw and make it clumsy here, because I am not a good I'm not good at drawing, but you can see it, you can understand that it is preserving that half wave symmetry. Now after this, what is happening here, when we are moving to hysteresis case, hysteresis here, see that even neither this output square wave is no more even nor odd, because the means reference time t is equal to 0, you have to consider it from the perspective of your input. Input will determine that which one is your zero crossing point or t is equal to 0. So from that you cannot understand whether this is having half wave symmetry or no, not half wave symmetry, whether it is having even symmetry or odd symmetry, we can't say. Here we can't. Only thing you can say is that it is preserving half wave symmetry. So that is the most beautiful thing of half wave symmetry. If your input is having half wave symmetry, it is very difficult to snatch that symmetry from your output. It will also follow that half wave symmetry, and that is why when hysteresis is present, all odd order harmonics are only present even at the distorted output produced by the element that contains hysteresis, right? So even if there is a distortion due to hysteresis, only odd order harmonics will be present. Only odd order harmonics will be present in our output supply or output curve, right? Now this is all about even, odd and other things. This will give you some understanding. Now in my I'm intentionally making it not exceeding the 1 hour, because this is a bit conceptual thing, and I want that all of you please practice it thoroughly and understand it. One more thing I would like to say, that in case just before I stop this video, I just want to tell you about space harmonics, because what is space harmonics? Suppose when you have a